The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So welcome back, and today I'm going to do some examples. What happens when you have more than one charge radiating? This is a very important example because whenever you have many charges radiating, if it's coherent, you get the phenomenon of interference. And it plays a very important role in many fields of physics, in particular in optics. You may have heard terms like interference patterns, diffraction, etc. All that is to do with it's to do when you have more than one source radiating. So the example I'm going to consider is the following. Suppose you have two charges, both Q. Each one is oscillating. It's oscillating with an angular frequency 2 pi over lambda. This tells you the position of the charge as a function of time. So it's centered the distance d from here, and oscillating with an amplitude a as a cosine 2 pi over lambda t, where lambda is, of course, the wavelength of the radiated electromagnetic wave. So this one is oscillating up and down like that. And there is another one over here oscillating, just for fun, in the other direction. This one is oscillating along the x-axis, and this one is oscillating along the y-axis. And here is the formula which tells you what is the position of this one at a given instant of time. They are both given in terms of the same time, with the same time t equals 0. Therefore, these are two coherent sources. The question is, what will be the resultant field anywhere in space? Some point we want to know what is the resultant field. Now, each one of these, you know what it does. It radiates a spherical wave with a certain angular distribution. All right? And the waves overlap in space. Now, because the electromagnetic waves are solutions of the electromagnetic wave equation, which is a linear equation, if we have a coherent source of radiation, at any point we simply add vectorially the electromagnetic waves. The electric fields you add vectorially, or the magnetic field. Now, in principle, we should go to first principles, consider Maxwell's equations, consider what happens when the charge is oscillating, and in fact consider both charges, what they're doing at any instant of time, and solve in all of space Maxwell's equation to see what the electric field is everywhere. We build on our experience, and what we will do is we will assume that we've solved the problem of what happens when a single charge is accelerating. We've done this several times in the past, and certainly Professor Walter Lewin has done it in the course. Whenever a charge is accelerating, it radiates. And this is the formula which tells you what is the electric field from a given charge which is accelerating at some position r and t. I'm just reminding you that what we find is that the electric field at any position at some time t is given by or related to the perpendicular component of the acceleration of the charge. It's perpendicular to the direction of propagation. But at a point t in space, the electric field there is related to the acceleration at an earlier time, at a time t prime, which is earlier than the time when we are considering, by the amount r over c. All that this does, it reflects the fact that if I have somewhere an accelerated charge, at that instant the electromagnetic wave starts to propagate, and it takes a time r over c to reach a distance r. That's all this is telling us. The other thing this is telling us, the wave front is a sphere. The amplitude of the electric field drops off like 1 over r. And it is not uniform in all directions, as we've seen in the past. Right? For example, if I take this charge, as it's oscillating up and down, the maximum amplitude radiated is in this plane, where we are looking, where the perpendicular component of the acceleration of this is a maximum, and its minimum upwards, it's 0, because this acceleration has no component of a perpendicular component to this direction. And similarly for this. The other thing which I wish to point out is that the polarization of the electromagnetic wave, the electric vector, is parallel to the perpendicular component of A. So from this, the electric vector, when it gets to here or here, will be in the direction of x, while from this one, it will be polarized in the direction y. The other thing which I want to stress, that we will, as in the other examples, always consider a situation where the point where we're looking at the electromagnetic fields is far away from where the charges are. The formula which I just showed you here applies only in the far field. Nearby, the electric field and the magnetic fields are very complicated. They can be calculated, but they cannot be summarized in a simple form. But if I am far away from the accelerating charge, then it is possible to write it in this simple form. So our discussion is only valid if the wavelength radiated is much smaller than the distance that we're considering. This distance is also much smaller than that, and this is to allow us to approximate sine theta by theta, etc. That's the case. All right. Okay. With that, we can now immediately solve the problem. Simply consider the acceleration of each charge from our knowledge of where the charge is. We can differentiate it twice, and we can get the acceleration. So we know that the acceleration of the the charge which is oscillating along the x-axis is given by minus a omega squared cosine omega in the x direction. I want to emphasize because this is in the same direction as the perpendicular component of A1. I'm sorry, I've misspoke there. The answer, what I said is correct, but for the wrong reason. In this case, by definition, the acceleration of the first one is this, because the displacement of the first one is in the x direction. Similarly, the acceleration of the second one is in the y direction, because the displacement is in the y direction. All right, so these are the two accelerations. This is just, occasionally I'll use omega, occasionally lambda, just to remind you of that. Okay, so all I now have to do for each of the charges, calculate this quantity at the position where I want to calculate the electric and magnetic fields. So first of all, in this problem, we're asked to do it in two places. We're asked to do it at position P1 and at P2. P1 is along the z-axis, and P2 is off the z-axis. First, let's do it for P1. So the electric field due to the first charge at position P1 at time t is given by this formula if I insert in this for the distance r, which is L, okay, and I put in the acceleration of this one, and the perpendicular component of the acceleration perpendicular to the line joining my two charges and the position P1 is, in fact, that line is along the z-axis, so the perpendicular direction is, in fact, in the x direction. Okay, so I don't even have to take the actual acceleration is the perpendicular component. Okay, and I have to calculate it at a time which is t minus the distance P1 is from my charges, which is L, so it's minus omega L over c. That's if I calculate t prime in here. Okay, notice I have not tried to calculate the distance between the charge and P1 exactly, because I told you that the distance d is very much smaller than L, and so the overall distance is negligibly different from being just L. Okay, so that's the electric field due to the first one. Similarly, I can do the same for the second one. Everything is the same. The only difference is between, in that case, is that now the electric vector, the acceleration is along the y-axis, and therefore the electric field is polarized along the y direction. So at the point P1, the two electric fields are the same. They're both oscillating in phase with the same frequency, etc. But this one is pointing in the x direction, this in the y direction. Now, as I mentioned at the beginning, if at any point you have electric fields due to two sources, they simply add, because the system is a linear system, so we simply have to add the electric fields. Electric fields are vectors, therefore we don't add them algebraic just as scalars, but we have to add them vectorially. All right, and so we take this vector and add it, and that gives us the total electric field at point P1. And simply from here I get E0 like that, which I can rewrite in terms of a unit vector. All right, this is a unit vector which is at 45 degrees. In other words, if that's z direction, x and y, it's at 45 degrees to both the x and the y axes. That's a unit vector. This is the amplitude of it, and this is the tell us what is the oscillating frequency and what is the phase. Notice, although each one of these sources radiated there an electric field of magnitude E0, when I add them, I did not get 2E0. Because as I mentioned, you have to electric fields are vectors, therefore you have to add them vectorially, and that's why you get here the root 2. Okay, so this is the first example which I've done. Now I want to take the same geometry, but calculate what is the electric field. See, what we've just done, we've calculated it here. Now I want to take the same situation, two sources oscillating coherently, but I want to look what is the electric field at the point P2. And I've taken P2 to be in the xz plane, but in a direction at an angle lambda over 8d. D is this distance, lambda is the wavelength of the radiated electromagnetic wave, all right? And I've taken this crazy number simply to make the arithmetic come out easy at the end. And so we now want to calculate the electric field here. And we do exactly the same, so I can go a little faster. What I will do is I will calculate the electric field here due to this charge oscillating. I'll then calculate the electric field here due to this charge. This one is oscillating like that. I'm reminding you this one is oscillating like that. And we will vectorially add the two. Now, from the point of view of the amplitude, the difference in distance between this and here, or this and here, or this and here, is insignificant. And so I have ignored that in the previous calculation, and I'll do the same here. But when you add the two, we have to worry about the relative phase of the alternating electric fields. And the difference of this distance compared to that distance is no longer insignificant when it comes to the relative phase of the two radiations. So in the formula, in this formula, when I'm calculating the electric field, this R, it doesn't matter whether I get here, call this L or L plus a little bit or less. This doesn't change very much. But in calculating the phase of the radiation, I cannot ignore that. In the previous case, the phase was the same because this distance and that distance are exactly the same by symmetry. For this position, that distance and that distance are not the same. And so I will have to what I will do is I'll use as reference that distance, and when I'm calculating this distance, I will calculate by how much I have to subtract from here to end up with this length, and for this one, by how much I have to add to it to get to here. I'm just pay attention to that when I'm doing it in a second. Okay, and the rest is very straightforward, similar to what I've just done. So now, as I say, I want to calculate the electric field at the point P2, which is this. This is the x-coordinate, y, and z-coordinate, and I pointed it to you a second ago. All right. So I don't have to rewrite all those q's and omegas, etc. By analogy with what we've done, the electric field due to the first charge at position P2 will be that the amplitude that we got the same for in the previous case at P1. So it's E0 is the amplitude. It's pointing in the x direction as before, okay? And we know that the description of the electric field will be given by cosine omega T1 prime, where so far I've always talked about T prime because I only had one, when I was considering just one charge. But here, the T1 is different to T2. So quickly, this term comes from the perpendicular component of A, right, as before. And T1 prime is equal to the time when I'm looking at the electric field, okay, minus the time it takes for the signal from the charge to get to the point where I'm looking at the electric field, to the point P2. So it will be what? As I told you a second ago, I'll take L as the reference, and I'm subtracting from it that distance d sine lambda over 8 over d. For a second, let me go back to that picture, because this is easy. You can easily get confused. So I'm coming back here. What we're trying to calculate, the time, the distance from here to here. So I'm taking this distance, which is L, and I'm subtracting from it this distance, which is d sine this angle here, which is the same as this angle. Okay? So that's what I'm calculating there. So this is L minus d sine lambda over d divided by c. Okay, then the electric field is then immediately follows from this. It's easier in the x direction. Cosine omega t minus this, okay? And if you assume that this angle is small, and I told you that that's given in the problem, the sine of an angle is equal to an angle, approximately, if they're small. And if I multiply all this out, I simply get an angle here. Okay, and that's pi over 4. So I find that the electric field at point P2 is pointing due to the first charge, is pointing in the x direction, as you'd expect, because of the direction in which the charge is moving, times E0 times cosine omega t minus omega c plus a phase like that. Okay, how about from the other charge? If I take the other charge, everything will be the same, except now this charge is oscillating in the y direction. So the electric field will be in the y direction. And this time, it's omega t2 prime, where t2 will be very similar to t1, but now the distance is greater by this amount. For a second, let's go back to this picture. So you see what I'm talking about. If I calculate this distance, all right, it's the same as that distance, okay, plus d sine this angle, which is this lambda over 8. Okay, and I'm subtracting it. Okay, and I want to emphasize that what I'm focusing here, what is important, is the difference between this and that, and not the absolute value. So when I'm approximating, if you do this calculation for yourself, you'll see I'm doing a slight approximation to calculate that, but this and this is the same quantity. Okay, but the important thing is this difference of this phase. Here it's plus pi over 4, here is minus pi over 4, because here it's minus that little bit of a distance, and here it's plus a little bit of that distance. Okay, so we finished. The total electric field at P2 and time t is the sum of the electric field due to the first charge plus due to the second charge. Okay. And as I mentioned a second ago, electric fields are vectors, that we have to add these two vectorially. Okay? This is in the x direction, this is in the y direction. And so what we have at that point is two oscillating electric fields. They are oscillating coherently, but out of phase. This is a plus pi over 4 phase. This is a minus pi over 4 phase. So the difference of phase between those two is pi over 2. It's 90 degrees. So this is out of phase with one with respect to the other by 90 degrees. They're coherent, but 90 degrees out of phase. The magnitudes are the same, but this one is pointing in the x direction and this in the y direction, and you know what that corresponds to. If I have at the location two electric fields, one doing that and the other one doing this, okay, if they're out of phase by 90 degrees and I add the two, what do I get? I get a constant size of a radius, and the thing is rotating. That is the description of a rotating vector of magnitude E0. In the other case at P1, there was not this phase difference, so the two were, one was oscillating like this, the other one was oscillating like that, but they were oscillating with the same phase, so this is what they were doing. And if you add those up, you get a line diagonally. And that's why before we got the result was a linearly polarized electric field there at 45 degrees to the x and y axis. In this case, these two are out of phase by 90 degrees. So when one is doing this, okay, the other one is also but out of phase. So when this one's at the maximum is minimum, and so that's what's happening. Okay, so they're out of phase, and then if you add the two up, you get something doing this, which we call circularly polarized light. And that's why I chose that crazy angle, because it came out like this. Okay, so that's the end of that problem. I'll now do another one, which to emphasize some technique, a different technique of doing it. Okay, let's move. So the next problem is the following. We're again dealing with several charges oscillating coherently. They're cohering sources, and we're asking what are the electric fields at somewhere in space. And if we found the electric field, of course, we could always calculate the magnetic field at that location using Maxwell's equations or our knowledge of the relation between the electric magnetic field in a progressive electromagnetic wave. Now I'll take three charges, okay? But that's not the hope. That's a small difference. But what this problem adds is I will use it to show a technique that is often used, which helps in the solution of such problems. So the problem now is the following. I have three charges, each of the same magnitude. They're located along the x-axis at position 0, minus d, and minus 2d. So these distances are the same, each distance d. Okay? And what the problem is, up to t equals 0, these three charges are displaced from equilibrium at y0, so at the height y0 here. Then, at t0, don't ask me how, magically, I get these 3 charges to start oscillating. Okay? Such that at time yt, the displacement is y0 cosine omega t. And this continues like that forever. The question is, as a result of this oscillation of charges, what will be the electric field a long way away from here at position L along the x-axis, so we call that position P. So the problem is calculate E at position P for all times. We could have, once we calculated, we could calculate the magnetic field, but to save your time, I mean, you can do it for yourself. You know, if you calculate the electric field, there's a progressive wave over here. If E is like this, then B will be perpendicular to it of amplitude, which is just a dE over C. So that will be straightforward, so I'm not asking it. Okay, now let's just think for a second what goes on in this problem. Initially, the charges are stationary, so there will be a Coulomb field around, but we are specifically asked, ignore static fields. So in the last problem too, I ignored the static fields. We were only considering the time-dependent fields. It doesn't, you can always have superimposed on a time-dependent field some static field. It just doesn't add anything. So what we have here is at time, up to time t equals 0, the charges are here. So let's take one of the charges here. Then it starts moving. It will have an acceleration which is perpendicular to the direction in which I'm interested in the propagation of the electromagnetic wave. Okay? So it will certainly radiate in this direction. So this charge, which is oscillating, will radiate. Over here, at the point P, the electric field will be initially 0, and it will continue being 0 until the electric field, which is generated here, propagates that distance. So only after a time L over C will the electric vector get here. So up to the time L over C, there will be no electric field here. How about this charge? This charge initially is displaced at y, 0. Then it starts oscillating. The same. Initially, it's stationary. It'll produce a Coulomb field, which is a static field. We're not interested in it. But once it starts accelerating, it starts radiating. And that radiation progresses. So that will also produce a field over here. But since these two distances are different, the radiation from here, first of all, will get there a little later. But also, once it gets here, it will have a different phase, because the radiation traveled a different distance. And same for the last one. OK, so now how do we do this? I almost sound like a broken record. As always, I can calculate the electric field from each charge, and it will be given by this formula, which we've seen over and over again, where T prime is the distance from the charge to the point P. Furthermore, I know the perpendicular, the acceleration, and also the perpendicular component of it, because in this problem, the perpendicular component is the same as the actual acceleration. After time t equals 0, the acceleration of every one of these charges, A1, A2, A3, is the same, it's in the same direction, and it's given by that simply because we know what is the displacement of y of t. If I differentiate it twice, I get the acceleration. If I plug this into here for each charge, I will know what is the electric field from each charge. I can then add the electric fields from each charge, and I'll get the total electric field. And I have to add them vectorially. All right, so once again, for t less than L over c, the electric field at position P will be 0. There was no earlier accelerated charge which radiated an electric field which got here before this time. Okay, so that's nice and easy. How about for a later period, a period between L over c, or just after L over c? For t just after L over c, the acceleration of the charge at x equals 0 would have produced an electric field which propagated, and it would have got to my point P. So between the time L over c and the time when the radiation from the second charge got to the point P, I will have an electric field, but only from the first radiation due to the first charge. I can forget the second and third, the charge at minus d and at minus 2d, but not the charge at x equals 0. So that will be, I use this formula, I plug it in, I use the acceleration of a1, I put it in here, and I know that t prime is t minus r over c. R in this case is L. So this formula immediately tells me that's what it is. And let me save, I don't want to write this over and over again, I'll call that E0. So from the first charge, this is what the electric field, it's an oscillating electric field, what it looks like at position P. But I'm reminding you, this is only true for this window, time window, when the radiation from the charge at q equals 0 has got to point P, but from the other ones not. How about for a little later? From the time L over c plus d over c, in other words, now a radiation over a distance L plus d has had time to reach my point P. So now this second charge, the one at minus d, has had enough time to reach my point P. But if I limit t to the window, this and that, in other words, there's still a difference of d over c in time between those, I will get at point P the radiation as from the first charge. That's exactly the same as this. That's obviously got there. But now from the second charge, it has got there. And they're very similar. They are both, the charges are accelerating along the y direction, all right, in phase, okay. So they have the same frequency. So it's and the amplitude is going to be the same, because in this formula, this r is the total distance between the charge and the point P. Now, there is a tiny difference in that distance for the first and second charge. But if I take in here a tiny difference, this will not change very much. I'm ignoring that difference. So I'm calling both of them E0 and ignoring that tiny difference. But I cannot ignore the difference of the phase. So the t prime in the two cases is different. In one case, it's t minus L over c, And the other case, it's minus L over C minus this little extra time where the radiation takes from the second to the first charge. Okay, and the third one, the radiation could not reach the point P yet. So that is now the total electric field from the two. Okay, and finally, and I have to do this, I haven't done the addition, and finally, if we take a time which is greater than this, then we are in a situation where the oscillation of the last charge has had enough time to get to the point P. Let me go back to this picture and just repeat this so that you don't get lost. So these charges have started to move all at the same time. After a time L over C, the radiation from this one will have got to here. If I add to it the time d over c, that's how long the electromagnetic radiation takes to get from here to here, so a little bit later, the radiation from this plus the radiation from this is getting here. And a little bit later, the radiation from this also gets there. So at the end, there is now radiation from all three charges getting to this point. And from then on, it'll continue forever as long as these are oscillating. OK. So from then on, you have the radiation from the three. And the only difference between them is they all have a slightly different phase. OK, so you might be satisfied with just knowing that these are the electric fields as sums of the algebraic sum between those. They're all pointing in the same direction, so I don't have to worry about the vector addition, but I have to worry about the addition of the amplitudes. If we want to find out what this sum is, what happens when you add 1 or 2 or 3 oscillatory functions like this, what is the resultant oscillation? We have to algebraically or trigonometrically add these 3 or these 2. And I did this example in order to introduce a mathematical technique which in situations of this kind makes life much, much easier than just going and adding cosines. And it is by using so-called complex amplitudes. So the issue is, how do we add these 3 cosine functions and where they each have a slightly different phase? One way is brute force. Do it by using trigonometrical formulae. For example, you can add the first to the second by using the formula cosine A plus cosine B equals twice cosine, half the sum of the angles, cosine half the difference of the angle. And you could do that for adding the first to the second, and then later, once you got an answer, you could add to that the third, etc. But you can see that if you have 5, 6, 7, 8 sources, or many, many more, this becomes cumbersome. There's a nice mathematical trick, and that is by using complex numbers. You know that this is De Moivre's theorem, that e to the j theta can be written as the cosine of an angle plus j sine of an angle. I can use this mathematical trick to solve the problem of adding these. Remember that at this stage, this is pure mathematics. It's, as always, we've converted an experimental situation into a mathematical problem, and we've got to solve this using mathematics. You don't have to ask yourself what's the meaning of j sine theta or something. It is a mathematical expression, and we're going to use mathematics to solve this problem. Okay, using this, I can always write that suppose I have a cosine of some function, I can always write it as the real part of e to the j that angle. So if I cosine, for example, of omega t minus kl, and you'll see it somewhere up there, for example, it can be written as the real part of e to the j omega t minus j to the kl, but that is the same as multiplying these. So it's e to j omega t times e to the minus j kl, where here I'm just reminding you what k, omega c, etc. is. Okay, I can do this for every, if I want to add, let's say we're doing this one first. I want this to that. I can write this as the real part of a complex number, and I can write this as a real part of the complex number. What I will then do, I will first solve this. I'll do the addition by adding the two complex numbers, knowing full well that if I added the complex numbers, I will have in the process added the real parts and also the imaginary parts. And since you cannot have real number equal to an imaginary number in any way, if I take and during the process of addition, I will have continuously kept separate the real and imaginary part. So, for example, for this third part, this addition here, I can write the first term as the real part of e to the j omega t e to the minus j kl in the y direction time e0. This is, of course, nothing other than e cosine omega t minus LC. The second one, I can do the same. This is the same, and the only difference between those two is that phase minus d over c, which is kd, using here. And so this, the real part of this will be the answer to the sum of those. Okay. So I'll do this in a second, but then let me immediately go to the third one, so I do both of them at the same time. And in this third case, the answer I'll want is the real part. This is the same as before, and here are the three terms. The first term is just E0 because all the phases are out here. The second one differs from that by minus d over c, which is minus kd, so it's e to the minus j kd. And the last one is e to the minus j times 2 kd, because here we have a 2d. Okay? All right. Now, why did I bother to do this? Because this addition is trivial, while the other one was not trivial, needed hard labor. Okay? Why do I say this is trivial? Because I've converted this algebraic problem into a geometry one. I can represent each one of these terms on a Argand diagram. So for example, here, let's take the third case. All right, where I'm adding these two vectors. This has only a real part, So it's E0. That's a vector of length E0 along the real axis. I'm reminding you that on an Argand diagram, okay, this direction is the real axis, and this is the imaginary axis. Okay? With that, so this E0 is only real. Okay? And I'm adding to it e to the minus jkd, which is what? Has a magnitude E0. And this is the angle, theta, with respect to the real axis, which in this case is minus kd. So this is the angle. So it's minus, so I'm going down. So it's a vector which goes, it has length E0, and it's pointing in an angle of minus kd. It's this angle, I suppose, not to confuse you, let me call it minus kd. Okay? This is minus and minus, just not to confuse you. Okay? So this and kd we found in this with the distance between the charges of d. Kd is 2 pi over 3, which is 120 degrees. So this term is a vector like that. And we have to add those two vectors. Well, this is easy to do. This angle is 60 degrees, if this is 120. Okay? And this length is equal to that. So the result of this plus that will be this red vector here, which has magnitude E0, okay? And at what angle is it? This angle here, okay, is 240 degrees. Okay? Actually, I'm sorry, I need that later in a second for the next part. At this, I don't need it at this stage. I'm sorry. I'm adding this to that. The result is this vector. And this vector has a magnitude E0. And this angle here is, of course, 60 degrees, which is 2 pi over 6. And so adding those two will give me just the real part of e to the j omega t, e to the minus jkl in the y direction, and adding those two is E0 in the direction of 60 degrees, which is minus 2 pi over 6, bracket missing. Okay, so this describes this addition. And this, of course, I can now take the real part of this whole thing, and there is the answer. E0 in the y direction, cosine omega t minus omega l over c, and with a phase of minus 2 pi over 6, which is, of course, 60 degrees. Okay, so for the first one, so this is the answer, and we didn't have to add any cosine. We just do the vector addition on the Argand diagram. Let's do the last case. In the last case, we have 3 terms. 1, 2, 3. If I write these as the real part of a complex amplitudes, by analogy with this, the first term is the same, the second term is the same, and the third one is almost the same as the second term, except the d has now become 2 kd. This was d over c, here it's 2d over c. So here we have minus j 2 kd. So now I have to add these 3 complex numbers. And again, this is much easier to do it geometrically than trigonometrically. The first one I can represent by this on the Argand diagram, the second one by this, And the third one, of course, is at 240 degrees to here. If this was 120, the next one is 240, and which means that the last one, all that it is, I remove this vector, and it's in this direction, okay? So now we're adding this to that to this, and even I can solve that in my head. If I add this vector to that, I get 0. I'm back where I started. So this quantity is 0. And so the electric field will be 0. And see how relatively easy it is to do if you use this complex amplitude method. One can do many problems to do with waves and vibrations using complex amplitudes. In general, it makes the algebra easier. But for most cases, I have not done that in order to, so that you don't have the double difficulty of trying to understand the physics and struggling with the mathematics that you may not be so familiar. By the time we come to many sources and the radiation, it is so much easier to do using complex amplitude that I would urge you to learn it on simple cases like this and then use it in more complicated situations. Finally, I just want to say one word, and that is the following. Some of you may be surprised, how is it that I have three charges, oscillating, radiating. How is it that when you get to here, you get, after a certain time, you see nothing? And the answer is, pictorially, you can see it. What happens? At this point, the radiation from one of the charges looks like that. From the second one, it's out of phase by 1/3 of a wavelength. And the next one by 2/3. And so you're adding 3 waves, 3 oscillating motions on top of each other. And if you add these, the result is 0. That is pictorially the same as what I did here in this diagram. They simply you do have 3 waves arriving from the 3 charges, but they add to 0 because each has a different phase from the previous one, and you can see it here, what happens. Here I'm plotting as a function of time the amplitude at the point P.